the great colonial powers of Europe dominated the world primarily through sea power. Surface fleets remained the most visible measure of strength, reflected in throw weight, penetrative fire, rate of fire, projectile range, and hit accuracy. As fleets grew larger and more sophisticated in design, sails yielded to turbines and wooden hulls gave way to iron and armor. As warships evolved, naval arms races intensified, driving rapid innovation. This relentless competition culminated in the emergence of the Dreadnought, the pinnacle of naval strength at the turn of the 20th century. In this video, we will chart a path of maritime innovation and explain how the world went from wooden sailing ships to the modern battleships which defined 20th century naval warfare. The age of sail, the modernization of naval artillery, began in the 14th century, when the introduction of gunpowder technology into European warfare led to the development of large cannons, increasing the weight of vessels, making or propulsion impractical, and paving the way for sailing warship. By the 16th century, the sailing man-of-war dominated the seas, featuring 3 masts with 3 to 4 sails. Their hulls reached up to 60 meters long, capable of carrying as many as 124 cannons, 4 at the bow, 8 at the stern, and 56 on the broadsides, capable of reaching speeds around 9 knots. By the mid-17th century, the line of battle tactic emerged as broadsides became decisive. Fleets formed orderly lines to deliver concentrated fire without risking friendly fire, shifting naval design away from vessels with heavy fore and aft castles suited to boarding tactics and toward lighter, more maneuverable ships. Hulls grew larger to accommodate more guns, giving rise to the ship of the line, with the common 2-decked 74-gun type weighing about 3,000 tons and mounting 24 36-pounder guns on the lower deck and various calibers on the upper deck. Despite these changes, 3 centuries of the age of sail saw little change in terms of protection and mobility. Consequently, an Elizabethan sailor from the 1600s could readily have served aboard Admiral Nelson's HMS Victory in 1805. The age of steam in the 19th century, the advent of the steam engine transformed naval propulsion. Steam power initially served as an auxiliary power source on ships, which were still primarily sail-powered. By the 1830s, navies experimented with paddle steamer warships, but their exposed, above-water paddle wheels hindered broadside fire. Between 1840 and 1890, Britain and France engaged in a naval arms contest known as the Great Race. To escape paddle propulsion, both nations turned to the Archimedean screw, a reversible hydraulic machine that could operate as a pump or a power generator. By 1846, Britain retrofitted 2 ships of the line with steam plants to create the first screw-driven ships, though these remained sail-first configurations. The French introduced the first true steam battleship, Napoleon, in 1850, with Britain replying with HMS Agamemnon 2 years later. For about a decade, wooden screw-driven ships dominated the naval race. The introduction of Paixhan's guns, capable of firing explosive shells, reshaped naval warfare. Demonstrated by General Henry Joseph Paixhan's in 1823 and adopted by France and other great powers in 1841, these groundbreaking explosive ordnances made wooden ships more vulnerable to shellfire. Screw-driven ships armed with Paixhan's dominated for a decade and saw action in the Crimean War, fought Russia, and an alliance of Great Britain, France, and the Ottoman Empire. The Russian Navy's destruction of the Turkish fleet at Sinop in 1854 underscored wooden ships' vulnerability to shellfire. In response, the French Emperor Napoleon III proposed ironclad floating batteries armed with Paixhan's guns to bombard Russian fortifications at Kinburn. This development marked a shift away from wooden ships towards ironclad vessels. France built its first ironclad, the Gloire, in 1858, while Britain followed suit 2 years later with the Warrior. Both retained square-rigged sails and broadside armament but were boiler-equipped, screw-propelled, armor-clad with about 4.5 inches of iron, and capable of global reach. Despite these advantages, their broadside layout limited fire fore and aft. A few years later, during the American Civil War, the famous clash at Hampton Roads between the CSS Virginia and USS Monitor introduced rotating turrets to naval warfare and sparked monitor mania, as European powers pursued similar designs. The French introduced turreted guns on barbette mounts, while the British adopted hydraulic systems enabling guns to rise and fall behind armor for reloading. Between 1860 and 1892, naval gunnery evolved rapidly. Calibers increased, range extended, breech-loading guns replaced muzzle loaders, and range-finding optics improved combat range toward roughly a mile. Warships began to favor 412-inch guns in centerline fore and aft. By the 1870s, wooden ships of the line had disappeared, replaced by heavier but less maneuverable metal hulls. Early reluctance to abandon sails lingered in Britain, where coal limits and reliability initially constrained steam adoption. However, boiler improvements eventually raised steam pressures, enabling efficient multiple expansion engines. Later, the steam turbine revolutionized propulsion, boosting power-to-weight ratios. Meanwhile, naval designers extended hulls and narrowed beams, achieving a 5:1 length-to-beam ratio by 1892. The steel era overtook iron with the Bessemer process and other advances in steelmaking, delivering lighter, tougher hulls without sacrificing strength. French ingenuity and technical prowess could not compete with Britain's vastly superior industrial potential and broader resources. After losing a war to Germany in 1871, France abandoned the Great Race and focused on its land-based army. Now uncontested, Britain deployed steel-hulled Admiral-class ironclads in the 1880s, arming them with large-caliber, long-range guns in open barbettes. The century closed with the advent of torpedoes and torpedo boats, offering a cost-effective alternative to mass battleships. The pre-Dreadnought era in 1891, Britain introduced the Royal Sovereign class, a balanced solution of power, protection, and propulsion. Displacing over 14,000 tons and exceeding 400 feet in length with a length-to-width ratio of about 5:1, these ships were powered by a pair of three-cylinder, vertical triple-expansion steam engines delivering a top speed of 17.5 knots despite their heavy armor. Their main armament consisted of four 13.5-inch guns mounted in two centerline turrets, complemented by a secondary broadside battery of 12 6-inch quick-firing guns and 12-pounder guns for anti-torpedo boat defense. This configuration defined the pre-Dreadnought standard for the next decade. The dawn of the pre-Dreadnought era coincided with Alfred Thayer Mahan's book, titled The Influence of Sea Power Upon History. In it, Mahan argued that sea power was the decisive factor enabling prosperous, influential nations to project dominance over weaker ones, and that naval supremacy was best achieved through decisive, fleet-wide battles. The book quickly gained breadth of influence, permeating military academies worldwide. As a result, the so-called Mahan Doctrine shaped naval strategy across many nations. The Anglo-German naval arms race, while France effectively ended its naval rivalry with Britain after 1888, Kaiser Wilhelm II and Admiral Alfred von Tirpitz pursued a German navy designed to exert a fleet in being and compel Britain to concede diplomatically in any potential conflict, rather than openly challenge Germany at sea. Germany's 5 successive naval laws clashed with Britain's Naval Defense Act of 1889, which established the two-power standard requiring the Royal Navy to match the combined strength of the next two largest fleets. This confrontation resulted in the Anglo-German naval arms race. In Britain, the 1901 program produced 8 King Edward VII-class pre-dreadnoughts, carrying 4 12-inch and 4 9.2-inch guns in turrets, in addition to 10 6-inch and 14 12-pounder guns. This was followed by the Lord Nelson class of 1904-05, which standardized three calibers: 4 12-inch, 10 9.2-inch in turrets, and 24 12-pounders. Germany's program spanned 1894-95 to 1900-01, with 5 ships each in the Kaiser Friedrich III and Wittelsbach classes. These ships were well protected, featuring 9 4-inch turret guns, quick-firing secondary batteries, and a heavier secondary armament of 5 9 inches. Later, the Braunschweig and Deutschland classes of 1901-1906 increased turret calibers to 11 inches and raised secondary guns to 6.7 inches. Pre-dreadnoughts remained widespread and saw action in diverse conflicts. Notably, the Russo-Japanese War of 1904-05 demonstrated their vulnerabilities and sparked shifts in strategy. In the Spanish-American War of 1898, American pre-dreadnoughts fought shore batteries at San Juan, while Spanish armored cruisers and destroyers fought at Santiago de Cuba. However, the decisive influence on future designs came from the Russo-Japanese War, where Russia and Japan clashed at Port Arthur, the Yellow Sea, and Tsushima. These engagements overturned prevailing naval theories, as battles began to occur at greater ranges. Plunging fire from above became a dominant threat, and naval architects increasingly argued that the all-big-gun battleship would define future fleets. The HMS Dreadnought, the passage of Germany's Second Naval Act in 1900, heightened the Admiralty's concerns that Germany sought war with Britain. In 1904, Admiral Sir John Fisher became First Sea Lord and launched a substantial reorganization of the Royal Navy. He also formed a special committee to design a new super battleship. Analyzing the Battle of the Yellow Sea and the Battle of Tsushima, the Fisher Committee concluded that 12-inch guns offered effective hitting power and accuracy, while 10-inch shells were comparatively ineffective. Fisher also noted that during the Battle of Tsushima, which was fought between Russia and Japan, the Japanese Admiral Togo had successfully crossed the Russian fleet's T, aided by superior speed. Based on this observation, Fisher pushed for the next battleship to mount 12-inch guns and to achieve a speed of at least 21 knots. The committee finalized the main armament layout and rejected superfiring arrangements due to concerns that muzzle blast could compromise the sighting hoods on turret roofs below. Propulsion shifted from reciprocating engines to turbines to reduce overall displacement by about 1,100 long tons, with up to 6 shafts under consideration. The design included longitudinal bulkheads to protect magazines and shell rooms from underwater explosions, motivated by the belief that the Russian battleship Tsesarevich survived a Japanese torpedo hit due to a heavy internal bulkhead. To prevent displacement from rising, the waterline belt thickness was reduced by a single inch. Hull, weights, and stability. In February 1906, amid extensive publicity, the HMS Dreadnought was launched, astonishing Germany. The Dreadnought's hull design largely followed the proven Lord Nelson class, with a slightly squarer midship section to accommodate greater displacement and high speed without enlarging overall docking dimensions. She had an overall length of 527 feet, a beam of 82 feet, and a draft of 29 feet at deep load, and displaced 18,110 long tons. The hull features included a large, flat bottom and nearly vertical midship sides, creating a knuckle line where the bottom plating extended beyond the bilge near the A-boiler room. Unlike earlier ships, Dreadnought introduced a raised forecastle and a smoothly curved stem instead of the sharp ram of pre-dreadnought. At the same time, the stern incorporated a long cut-up to house the propeller and rudder arrangements necessitated by turbine propulsion. This fuller hull section helped dampen roll, contributing to somewhat improved stability and a slightly faster roll rate than its predecessors. Machinery and propulsion. The Dreadnought was the first battleship to use turbines in place of triple expansion steam engines. She was fitted with 2 paired sets of Parsons direct drive turbines, each driving 2 8-foot, three-bladed propellers, powered by 18 Babcock and Wilcox boilers. This achieved 23,000 horsepower, allowing her to reach 21.6 knots. Turbine propulsion enabled speed gains without destabilizing the overall balance, making turbines as revolutionary as the weaponry. It was also cheaper, quieter, lighter, more fuel-efficient, less prone to breakdowns, and its machinery was easier to place below the waterline for protection. All in all, the Dreadnought demonstrated the turbine's superiority for warships, establishing a standard for the next 6 decades. Steering and control to mitigate maneuvering issues caused by small, high-speed propellers, Dreadnought employed twin balanced rudders, mounted directly behind each inner propeller. This expanded the rudder area and boosted handling above 10 knots, but it came at the cost of reduced astern power and reduced steering ease at low speed. Electrical systems and ventilation. The Dreadnought's electrical power relied on 4 Siemens dynamos supplying 410 kilowatts, driven by steam engines, with diesel-driven dynamos providing emergency power to ensure operation if the boilers failed. 2 of the dynamos were driven by Brotherhood steam piston engines, and 2 by Merle's diesel engines. The latter provided the ship with an independent power source in case her boilers were out of use. Almost all auxiliary machinery was electrically driven, reducing the need for steam piping through bulkheads. Diesel engines initially suffered vibration and reliability issues, with one port engine replaced by a steam engine during service. Unpierced bulkheads mandated that each compartment have its own ventilation system, consisting of supply trunks with electric fans and natural exhaust outlets such as hatches, trunks, and skylights. Early trials showed that Dreadnought's magazines could reach temperatures of 100 degrees F, risking cordite performance. Thus, 2 steam-driven carbon dioxide plants provided cooling systems for each of her magazines, reducing temperatures to 80 degrees F, a crucial factor for consistent fire control performance. Accommodation and living spaces. The Dreadnought's complement was 700 in 1907 and increased to 810 by 1916. Traditionally, officers were housed aft with sailors forward, but Dreadnought reversed this arrangement so that her officers were closer to their action stations. It was unpopular with the officers because they lost their quarterdeck and were in proximity to noisy auxiliary machinery. The arrangement survived a few years, but the King George V class of 1910 reverted to the traditional arrangement. Armament. The Dreadnought's armament consisted of 10 Vickers 45 caliber 12-inch Mark X guns in a mix of wing and central mountings, with a primary goal of delivering a heavy broadside while maintaining manageable structural load.